And so let's go ahead and look at bitmasks. Bitmasks are a way of interacting with specific bit locations in your data or your values. Bitmasks you can think of as masks that you would put on your face, where they would cover specific parts and show other specific parts. So, for example, a mask would cover pretty much all of your face and only show your eyes or your mouth or whatever. The same concept can be applied to the bits of our values. If we only want to modify or show the first bit or the third bit or the fifth bit or etc., we can use a bit mask cover the um, to cover sort of all the other location of the other bit locations and only show that, for example, the first, third, or fifth one. And so let's go ahead and interact with bit masks and see how they can be useful to us. And so in C++, we can actually use specific binary values with the 0b prefix. And what this will do is it will tell the compiler that we actually want to use a literal binary value. And so the way I'm going to use this is, first off, I'm going to print the bit set of data, just so we can see the normal value and binary for it. So then I want to print, let's just say the second bit location. What I'm going to do is cout bit set 8, and here's what I'm going to do: 0, do 1 0. I believe that's correct. And I'm going to put this in parentheses, and that should work. So let's run this. Okay, yep. And as you can see right here, I'm printing a second bit in a set of 8 bits. And the reason this works is through the 0b prefix. 0b will tell the compiler that we want to print a binary set. And what it will do is before this 1 0 here, you can essentially just replace this 0b with a bunch of zeros, a bunch of 8 zeros that come before whatever you put before 1. So if we were to change this to just a single 1, it would print 7 zeros before this 1, and so this would change into 0 0, and then the 1 would be on the end, because we only have one number right here, and it's we only have one number. It's going to print or put 7 zeros behind it. And let's actually show that right now. And again, as you can see right here, it does what I said it would, because again, this 0b essentially just states to the compiler that we want to put a bunch of zeros before this number. And so because we want to print the second one, we would put a 0 after it. And if we wanted to print the third one, we would put another 0. And if we wanted to print the fourth one, we would put another 0, and so on. And we can exemplify that here. And now the fourth bit is being printed. But in this example, we just want to work with the second bit in this location. And so here I have an example where we're using the bit mask to detect whether or not the second bit in data is turned on or not. So what I have right here is the data binary value, and then the bit mask right here. And then what I'm doing is I'm doing a bitwise AND comparison. So if you remember, the bitwise AND comparison is going to change the bit values that are present in both values. So because these zeros are not turned on and these zeros are not turned on, it's not turning on either of these. This bit value is turned on, but this one isn't, because our bit mask is only doing this bit, the second bit, the second least significant bit. That is the only bit value that's turned on, not any of the rest of them. So it's going to be checking whether or not these two bits right here are turned on or not, because the AND is going to detect, hey, these two bits are both turned on, and it's going to set the value of that, which is going to be 2, because 0 0 0 0 0 0 1 0 is going to be 2. And so if it's going to be greater than 0, then it's going to be set. Otherwise, it's going to be the value of 0 because none of these are going to be turned on after the bitwise AND operation. So let's go ahead and see how we would set that bit. So let's go ahead and put a new line right here. And then what I'm going to do is I'm going to do a bitwise OR assignment. So data or equals, and then I'm going to do it'll be 1 0, and then I'm going to print out the new value of data. All right, and let's see what happens. All right, and as you can see right here, because we did not have the bit set, we set an OR compare in bitwise OR assignment to the bit mask. And if you remember, bitwise OR, it'll detect whether or not a bit is turned on for either value. So whether or not either of these are whether or not the bit is turned on for either of these, it will turn that on regardless of whether or not it's only turned on for one of them. And then it's assigning that to data. So it's actually changing the bits in data. And so now data will have that second bit turned on. And so let's go ahead and look at another example where we want to shift the rightmost bit, for example, in data, to the left, and we want to shift it once towards the left. So what that's going to look like is we want to get data to look somewhat like this: 0, 0, 0, 0, 0, 1, 1, 0. So how would we do that? Well, we want to shift the rightmost bit once over, and we don't want to shift the rest of the bits over along with it. We want to keep them where they are. So how would we do this? What would be our way of performing this operation? Well, let's look at our bit mask. We have a bit mask where we have the last bit turned on. So what would happen if we do data and mask? Well, what that's going to do is it's going to only evaluate to the last bits because they are the only ones where the last bit is turned on for both values. So let's think of something else. Well, we know that with the bitwise AND operator, it's going to evaluate to the bits that show for both values. So instead, what if we just want to try to get only the third bit, turned on instead of the last one? Well, we can flip all the bits in mask so that the mask value is turned into 1 1 1 1 1 1 1 0. And so when we do that and then do our AND operation, only the third bit in both values will line up. They'll be present for both values. So let's go ahead and do that. Let's get our last bit turned off. And so what this is going to do is it's going to turn off that last bit, so then now it's 0 1 0 0 instead of 0 1 0 1. And so because we're actually wanting to change the value of data, we're actually going to do an assignment. Data equals data bitwise and then bit flip mask. So again, what this is going to do is it's going to change all the zeros to ones, and then it's going to change the single one to a 0. And the reason why we are doing that is because we want to get the third bit lined up with the mask so that we turn off the last bit because the last bit is what's turned on in our mask, and we want to do the opposite of that. So that's why we are doing this, because we want to have the third bit now the only bit that's turned on. And so what comes after this? Well, now that we have our third bit turned on and all of the rest of them are turned off, now all we need to do is get the second bit assigned to data. And so the operation that we do with that is the bitwise OR assignment. If you remember, that's the pipe and then equals. And so what that's going to do is that's going to actually change the value of data, and it's going to set the bits to whatever bits are being found in either value. So either in data or the other value. In this case, it's going to be mask. However, if we just do this normal mask, it's going to just reset the 1 back into our last bit. We don't want to do that. We just reset that bit in on this line. So we know that the last bit in this mask is turned on. So instead, what we can do is we can shift this left once. And so what that's going to do is it's going to change the value of the mask into 000, 000, 10 instead of 01. And so when that's shifted left, it's going to assign this bit because it found this bit in this evaluation. It's going to assign that to data. And so let's go ahead and print the bitmask, or the bit set of data. Cout bit set 8, and then data, and then let's go ahead and see what that looks like. And as we can see, 000, 110. Now we've shifted this bit over without having to shift the rest of them. And so let's go ahead and clean this up a little bit. I'm going to go ahead and delete this line, delete that line, and then I'm just going to set data is equal to data, and then we flipped the mask in order to line up the third bit with both of them, and then we're going to assign that to mask, which is shifted left once. I'm going to put a parentheses around that, and then I'm also going to put a parentheses around both of these. And that should do it. And then semicolon right here. And that should do it. And then let's run it again just to make sure. And yes, again, it does. We have shifted our leftmost bit over. So I know this may seem very challenging, very confusing. Trust me, it is very confusing. It is not very intuitive when you're just learning it. It is something that you're going to have to do a lot to get used to. Even people who do it for quite a while still need refreshers on it and still need practice a lot of times, just because, again, it is not very intuitive as humans. We don't normally think like this in terms of logical bitwise arithmetic, as I would say. We think more in terms of just whole numbers, and adding, subtracting whole numbers. Changing values of whole numbers. We don't think in terms of how do we add a 0? How do we add a 1 to 0, 0, 0, 1? How do we add ones or zeros to a set of zeros and ones? We don't normally think in terms of computers. So it does take a lot of practice, and becoming more intuitive with bitwise operations in order to get comfortable with this. So do not feel bad if after all this, if things still seem confusing.